All right, we are in our last section for new content. So 10.5 is the last section. We've got 2 days of notes left, and we're talking about areas. So remember, in the rectangular coordinate system, if we want to find an area of a region bounded by A and B, we take the integral of the function, and the integral of a function just means that you're adding up basically a bunch of rectangles, and we've allowed delta x to get infinitely small, right? So the area of a rectangle is the height times the base, or the f of x times the delta x. We're doing the same thing, but we're looking at polar curves, and polar curves are not built on a rectangular coordinate system. They're built on the polar coordinate system. So instead of rectangles, we have these little sectors, like these slices of a circle, or a curve, I should say. So we're still adding up a bunch of sectors, but we need to remember what the area of a sector is. So if you don't have this written in, area of a sector is 1/2 times the radius squared times theta. And so the radius will be some sort of a function, right? The radius will be the r equals whatever function. And when we say times theta, we're going to be talking about d theta or delta theta, just like we were talking about delta x, so d theta. So our formula here is the integral from, instead of a to b, we're talking about angles, so alpha to beta, of 1/2 r squared d theta. R squared, like I said, will be some sort of a function. We're assuming that the polar curve is continuous and non-negative on the interval 0 to 2 pi for whatever the difference for alpha to beta is. So alpha is the smaller angle and beta is the larger angle. Okay, so let's try this. Find the area of one petal of the rose curve given by 3 cosine of 3 theta. So first we need to graph this thing. And remember, you can either sketch the graph or come up with a table of points. I like to sketch the graphs. I'm kind of quick at that. So I know the period is 2 pi over 3. Divide that by 2. Halfway is pi over 3. Divide that by 2. Pi over 6. Then 1 pi over 6. 2 pi over 6. 3 pi over 6. Pi over 2. Amplitude of 3. No shifts or anything. So boom, boom, boom. I may need to sketch more of this graph, but I will figure that out when I get there. I don't really need, well, so I won't elaborate on that yet. Let's graph what we have so far. Base 0, go out 3 units. Go back to the pole at pi over 6. And then face pi over 3, which is here, and go backward 3 units. Now I'm out here. And then go back to the pole at pi over 2. And then face 2 pi over 3, go forward 1, 2, 3 units. Now you can probably, without graphing the rest of it, just kind of knowing how these go, I'm going to go back to the pole for my next point. And then where do I have to go from here besides just where I meet the next value? Okay. But if you want those other points, it's like, okay, remember every tick mark is pi over 6. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6 is where it hits 0. And then the next angle, 6 pi over 6 is pi. That's where we must get down to 3 again. So face pi and go back 3, yes. Now I don't really need the full polar curve, but it is good to know that there are 3 petals if I needed to find the area of the whole thing. And I can rely on symmetry and set this problem up several different ways. So use symmetry. What do I mean by that? Well, each petal is symmetric, right? Like this petal, the first part that I sketched on there that went from, this was theta is 0. And then this was, where did we hit 0? Pi over 6. So from 0 to pi over 6, that area would be half of a petal. So I could say I'm going to double the area from 0 to pi over 6 of, of my formula for area of a sector, which is 1/2 r squared, 3 cosine 3 theta squared d theta. So what I've done, when you're finding area, you start at the pole. It's like this. You start at the pole and imagine there's a sector that hits that piece. And then there's another sector here and here and here. So you're finding that area, doubling it. That should give me the area of one petal. Now you can work on this. Pull this 1/2 out so the 2 really isn't there. Go ahead and square. You get 9 cosine squared of 3 theta d theta. The 9 can get pulled out in front. Okay, now what about this? How do we integrate cosine squared of 3 theta? There are 2 trig identities that you do need to have memorized if this is a non-calculator part of an AP test. So if this is a calculator part, this is easy. I'm done. I'm typing it in, going on from there. But if it's not, I need to know formulas. So these are the, what are these? Power reducing formulas, I think. Cosine squared of u, some angle u, in our case it's 3 theta, is equal to 1 plus cosine of 2u divided by 2. And here's the other one we need. Sine squared of u is 1 minus cosine of u over 2. So they're the same formula. Cosine is plus, sine is minus. All right, so how does that help me? Here, it tells me I've got 9 times the integral from 0 to pi over 6. Instead of cosine squared 3 theta, let's apply this formula. So u is 3 theta. That means that 2u is 6 theta. So I can make this 1 plus the cosine of 6 theta over 2 d theta. Okay, how does that help me? Well, I can work on this, right? Let's put the 2 out in front. No need for extra constants. 1 plus cosine of 6 theta d theta. I can take the integral of 1, and I can take the integral of cosine of theta. Just remember, you've got a little u sub going on, right? Cosine of u, how am I going to get u du? U is 6 theta, so du is 6 d theta. So there's going to be a 1/6 to get that d theta. All right, so see if we can piece that all together. 9/2 is out in front. The integral of 1 is theta. The integral of cosine of 6 theta needs to have a 1/6 out in front. Is it a plus or a minus? Let's see. The integral of cosine is sine. So it's a plus 1/6 sine of u, which is 6 theta, evaluated from 0 to pi over 6. Okay, 9 over 2. Let's plug in pi over 6. So we get pi over 6 plus 1/6 times the sine of 6 times pi over 6. The sine of pi is just 0. Minus, plug in 0. Everything's 0 there. Okay, so this is, let's see, divide by 3. 3 pi over 4 plus 0, right? So just 3 pi over 4. So the area of one petal is 3 pi over 4. Now, the reason I say I didn't have to graph the whole thing, if a follow-up question was, what's the area of the entire thing? As long as I know there are 3 petals, or as long as I can figure out, based on how much I need to graph, that there are 3 petals, I can just find the area of one petal, multiply it by 3, and get 9 pi over 4. And I want to make sure that we know that that's not just me saying, oh, we'll just go around a full circle, 0 to 2 pi of 1/2 r squared d theta. If I went from 0 to 2 pi, I wouldn't get 9 pi over 4 because remember, we did graph this whole thing and we got there in pi units, right? So if I were to go to 2 pi, I would be tracing the graph over itself and I would get double the area. So that would not be accurate. Now you can, this paragraph I'm not going to read through, but you can memorize some patterns for like, well, when it's cosine and the angle is this, it's going to have this many petals. When it's sine and the angle is this, it's going to have this many. It's probably not that hard of a thing to memorize, but I just find it just as easy just to kind of go through the math. So anyway, you can read that if you're interested. But one other thing that this does say at the bottom, now I don't know if you have this written in or not, but since I know if I were asked to find the area of the entire, like all 3 petals, I could find the area of one petal and triple it. Or if I do graph the whole thing and I figure out that it completes its graph from 0 to pi, then if I set up the 1/2 r squared d theta from 0 to pi, excuse me, then I would get the correct answer. So you can do the whole thing. You just have to know the limits of integration. All right. Find the area of the rose curve given by 2 sine of 3 theta. So again, if you follow those rules up there, this is going to have 3 petals, but we can also just graph it. Things going on. I like to graph this. Pi over 3. Cut that in half. Cut that in half. 1 pi over 6, 2 pi over 6, 3 pi over 6. It's a 2 sine. So 2 to negative 2. Sine starts at 0 and goes up, 0, down, 0. There's my sine curve to get me started. And it's find the area of the curve. So that's all petals. All right, so start at 0, face 0 and go 0. Face pi over 6 and go 2. Hit 0 again. Face pi over 2, but go backward 2. Hit 0 again. I can probably kind of guess what's going to happen, but if you need to plot more points, you can. So my last point here, again, if I want to graph the whole thing, my next point would be, where are we? Let's see, 1, 2, 3, 4 pi over 6. At 5 pi over 6, I'm going to go up. So at 5 pi over 6, I'm going to hit 2. And then I'll come back to the pole, which is where I started. So where do we finish? We finish at pi. So I have a lot of options here. If I don't know just by looking at the equation how many petals it has, then I can graph the whole thing and say the area is 1, I like to pull the 1/2 out in front, by the way. 1/2 times the integral from 0 to pi, that's how long it took to complete the whole thing, of, let's just go ahead and square this, 4 sine squared 3 theta d theta. Pull the 4 out in front. Instead of sine squared 3 theta, let's make it 1 minus cosine of 6 theta over 2. Get that 2 out of there. Okay. Integrate this, similar to what we did before. Theta, we're going to have a 1/6, right? And the integral of negative cosine will be negative sine. So minus 1/6 sine of 6 theta from 0 to pi. So pi minus sine of 6 pi is 0. So pi minus 0 minus 0 minus 0. I always check that because, you know, if this is like a cosine or something somehow, then it don't matter. So I get pi for my area. Let's write down some other options. Maybe you know this is going to have 3 petals. Another option could be 1 petal, like 1 petal full. It doesn't have to be the first petal. It could be any petal. So a full petal, like, I don't want to say that, like, this petal completed itself. Let's see, we went from, started at 0, right? Then we went out and we hit the pole again at pi over 3. So in the previous one, when this petal was on the axis, it's technically like finished at the end of the period, so you wouldn't want to use that petal. But anyway, I could say I'm taking the area of 1 petal, and there are 3. So 3 of these petals times 1/2 the integral from 0 to pi over 3 of 4 sine squared 3 theta d theta. the math is going to work out the same way. You're still going to get pi. I'm not going to go through the whole thing, but that's a way to set it up. Or you could go one more step and do, that one was times 3. You could do 1/2 petal, double it, and then triple the petals. What would that look like? A 1/2 petal would be, okay, I've got 3 of these things. I'm going to have to double them, and there's a 1/2. A 1/2 petal was 0 to, where were we right here? 0 to pi over 6. I'm just going to write r squared d theta. Okay, so it's kind of interesting. They're all slightly different variations. There are a lot of ways to get there. Whatever you think of first, that will get you to the correct answer. Ultimately, the antiderivative piece turns out to be a similar process every time. Okay, here's something that's a little different. Find the area inside the leaves of this polar curve and outside the circle r equals 1. So let's sketch the graph first to see what we're talking about. First of all, the circle, r equals 1 is here. And then what about this? So let's see, 2 sine of 3 theta. Wait, did we just do that one? Oh yeah, okay, sorry. I'm just going to copy the graph that I have from above. We don't need to take time to sketch that out. So that was this and loop and loop. Okay. Find the area inside the leaves, outside the circle. So like this. And here. And oh, and there. So what do we need to know? Well, there are 3 of them. So I'm going to do 1 leaf, multiply it by 3. I have options again. I can do half a leaf, a full leaf, whatever. I'm going to do 1 leaf. So I need to know what is that point and what is that point. What's that theta? What's that theta? Let's solve for that algebraically. When is this curve equal to this curve? R equals 1, R equals 2 sine of theta. So when is 2 sine theta, 3 theta, excuse me. When is 2 sine of 3 theta equal to 1? When sine of 3 theta is equal to 1/2. When 3 theta is equal to, now these are quadrant 1 angles, right? So don't bother with quadrant 2. 3 theta is equal to, you're going to get pi over 6. Well, sorry, I should elaborate. Don't bother with quadrant 2, meaning you don't need to go all the way around the circle. But I do need to get 2 angles here that are still within quadrant 1 when I divide by 3. So, okay, so ignore me, basically. 3 theta is pi over 6. 3 theta is 5 pi over 6. Theta would be pi over 18, quadrant 1. 5 pi over 18, still in quadrant 1, right? Because 5 is not half of 18 yet. This would be 9 pi over 18 up here. So those are the 2 angles. This is pi over 18 and 5 pi over 18. I could figure out this angle. It's halfway between the 2. Or I could figure out like, well, when is that curve equal to 2? But I'm also just looking at my graph, and that was pi over 6, right? So I'm going to do 1 leaf times 3. I could do half a leaf, double it, and then multiply that result by 3. Okay, so 1 full leaf times 3. 3 times the 1/2 I'm pulling out times the integral from pi over 18 to 5 pi over 18 of r squared. I'm sorry, it's r squared minus the circle, right? So when I say r squared, the first r squared, that's the area you're getting is for a full petal from the pole out to each point on that petal. So I kind of need to scoop my work over. Let me pull this down. Sorry, I know you can't really do this if you already started writing there. I just don't want to run into that work. So, all right, so I have the integral of 4 sine squared 3 theta d theta. So that's 3 petals right now, right? Why did I say leaf? 3 petals. But I need to subtract out the blue area. I need to take out the area of that little sector of the circle. So I also need to subtract the area of the circle. So where did I go? Oh yeah, sorry. So -1. I don't have to do it separately. I can do it all in one. -1 d theta. That's, we'll call it like big R squared minus little r squared. Kind of that same thought with our areas. I was about to set up a full different integral, which I could do the same thing, but just have like 1 d theta, and that I was just checking on that, make sure I didn't have to do that. That seemed kind of silly. Now I would use a calculator on here. So in doing this, you don't have to be in polar mode. I would just say 3/2. I mean, you could be if you wanted to. This one's not too bad to type in. 3/2 times the integral from pi over 18 to 5 pi over 18. And then in here we have 4 times, careful with signs squared. You need parentheses first, and then, oh my gosh. You need parentheses first, and then you need, hitting all the wrong buttons here. There we go. And then you need sine of 3 theta. Close that, close parentheses around sine, square it, d theta. All right, so I'm getting 2.906. All right, so when I'm looking at